Alright, so we will get started. My name is Riccardo, thank you for coming, and I'm here to talk about functional reactive programming for natural user interfaces. So, the original talk is a couple hours, so I try to narrow it down as much as possible. However, I'm going to focus in FRP, and I'm going to cover the natural user interfaces. I have a game at the end. I'm going to play with leap motion. Anybody familiar with leap motion? That's a cool announcement. So, this is actually, this is not my classic talk, right? I usually talk about other topics. But this is like a journey that I had when I work in a project that I want to implement FRP. And I initially did in F#. It was such an old library in F#. Anybody familiar with F#? All right, cool. So in the talk, I'm going to cover one language and enough, meaning that it's going to be a little bit also another language. F# and C#. And C# probably is not the language to go in a conference like this one. But the main idea is that this concept applies for any kind of languages, right? And if I can do in C#, you can do in language, right? So the agenda, we're going to cover what is FRP and try to clarify some terminologies. The foundation motivation, and then I implement FRP using the original paper and the more modern paper. It'll be clear later on in the presentation. And then we're going to play with emotion. I'm going to play with emotion. But all the code is on GitHub. So in the end, I'm going to provide a slide. And I don't want to make a classic, boring 60 minutes. We're going to have like a full hour together. Are you sure? Okay. So all slides, right? So I'm planning to do probably like 20, 25 minutes slide, a lot of code sample, then 5 minutes recap for the new implementation, then the rest is going to be, again, code sample. Is it cool? All right, boring slide about me. I'm Mexican from Italy, very much. So forgive me if sometimes I start to speak faster when I'm excited, right? But yes, and I do a lot of things. But we are here because of this. So, how many of you are familiar with the FRP? Right, cool. And how many of you are deep core Haskell programmer? All right, cool. So, how many of you familiar? Well, think that building DSL to expand host languages to provide benefit to solve a specific domain. All right. How many of you are awake? All right, cool. All right, let me go. So FRP. So what is FRP? And this is not an easy answer, right? Because there are in academic side of the industry that treat FRP as a value that's changed over time. And then there are other side of the industry that treat FRP as some sort of umbrella set to different kinds of terminology, right? And there is some confusion, and I think because these three words there, if you try to combine these three words, you get different kind of terminology, like functional programming. Right? So I'm not going to give a definition, but everybody knows this one. Right? And everybody loves the rules, or programming rules. The functional programming allows like side effect free, immutability, and composition, right? But if you play a little bit more further with this word, we have reactive programming, right? And it's sort of become ubiquitous, right? If you're building any sort of application where you treat real-time component, well, you most likely be exposed to reactive techniques, right? And the confusion, I think, is to the fact that some people, not people, but some people think that if you can apply other operations such as map, filter, and so forth on event, you're doing functional reactive programming. This is not true, right? There is, however, a relation between functional programming FP and functional reactive programming FRP. I mean RP, reactive programming. To the fact that reactive programming uses functional construct to achieve composable event abstraction. So this is F#. You can see I tweet receive just a string, an event. It can start to pipe and apply out operation against this event, right? And then finally, we can combine all these three words together. And we have functional reactive programming, which is really a subset between both functional and reactive programming, right? But when we're talking about FRP, we're talking about a paper written 20 years ago by these two cool guys here, Cornell and Paul Hudak. Functional programming, we're going to discuss pretty much all this hour, but it's all about composable, dynamically evolving values over time. Which means you can get value that change over time, but you avoid the mutational state, right? It's about to focus on integrating time flow and the compositional aspect of the event, but still enforcing the functional programming rules. So this is the talk. Everybody like this talk? Or everybody wait? So this is the original paper. Who is familiar with this paper? All right. It's like written in 1997, which described FRP as the paper actually described how to implement a library in ASCO called FRAN as a functional reactive animation, right? Really to deal with interactivity between 2D, with 2D or and 3D graphics, right? But the whole point is that FRAN is based on the notion of two polymorphic data types, behaviors and events, which they'll deal really with values that change over continuous time or discrete time. So this concept is still used today in behavior and events, right? I think the talk earlier today talked about a few things. But for instance, am I familiar with Elm? So Elm use they call it signal, right? But the idea is applied to functional programming. All right, and really it's a paradigm that provides elegant way to express computation domains such as robotics, animation, and so forth. And main goal is really reducing the complexity that compared to a traditional stuff. And special attention in these days with virtual reality, everybody like HoloLens or HoloLens and so forth. But what is interesting is that functional reactive programming really doesn't apply only to animation, right? But for instance, in the stock market, you think about it, like the price change over time, right? So, but why? Why FRP? Anybody want to give a guess? Anybody? Because we love composition, right? It's about provide simple, pure composable semantic for building complex structure based on very few primitives, right? And using combinators. And these building blocks are our behavior and events, which I'm going to discuss in a few slides. So first of all, composable semantic. Then think about another reason, right? Let's consider a list comprehension. Here we have C#, right? And the same logic implemented using link, right? Yeah, F# and so forth. But the idea, we can create operation against list from the scratch, or we can apply existing higher-order function, right, such as filter and map. And we can use this primitive individually, really by composing them. In this case, use the type operator. And this is a super still example, but high level, you get the idea, right? We only want to raise the level of abstraction and program against, in our domain using embedded DSL, right? So we really want to define a precise DSL to solve the problem for our domain. And FRP provides this kind of DSL, right? We want to have some sort of combinators to combine our building blocks using high-order operations such as list map or list filter, right? And we're going to build this component. And last, anybody want to guess? Guess they're so shy. What is the pyramid of shame, I call it?
Pyramid of doom.
Yeah. So, usually in imperative programming languages, or JavaScript, you deal with change of model over time in two ways, right? With mutable states or using callbacks, right? And everybody loves callbacks, especially the nested one, right? What can ever go wrong at the end, right? Just keep following. He's fine. I called the owner, he's completely. So, avoid callbacks, DSL, and composition. Bonus feature is quite awesome. I really think it's a fascinating topic. And again, this is not my really branch of expertise. I just love the concept about model things like the user can input in like animation and so forth in a very explicit manner. So, wow, slide 20. Now, finally, what is FRP, right? So, FRP is a paradigm for building reactive system and provide composable abstraction over dynamic stuff. And it really and this value a very precise denotational semantic, right? Anybody notice denotational semantic? Well, it's a pretty simple concept, but well, I think at the next slide we'll cover that. But there are two main ideas that shape functional programming. First, the denotative, right, which means that you use compositional semantic to specify the meaning of each type in building blocks. And then with the temporary continuous, which focus more on the composition aspect of FRP and how use a compose correctly this building block to achieve our FRP animation. So, the notational semantic is a really mathematical expression of the formal meaning of your program or programming language, right? It's the idea that it's interested to express the intention of the program, not describing what's up if you execute your program, but most likely try to translate the native language you're using in a more mathematical representation. So let's consider, this in the slide here, the factorial function, right? So this is pretty clear. It's an expression from 1 to n, which is a list of integer, and a function product, the multiplier element, right? So pretty much it comes from the mathematical, right? So we know the intention here. This is the same implemented in C. So I think it's pretty clear which language has a more strong, actually probably has, the notational semantic. And the notational semantic fit quite well in FRP, as described in the paper, because it's used, and that's actually what I really learned from this experience, how you use the notational semantic to express and create a very elegant vocabulary around your API, right? It's some sort of don't get sloppy, right? So really use a good convention to create your DSL. And the reason because the notation semantic leads to simple design, right? And simple design, with simple design you can achieve, it's easier to reason about what you're doing, your intention, right? It gives you the opportunity to reason further down and create a more complete library. All right, so now we talk about a little bit what is FRP. Any question? By the way, if you have any questions, just yell at me. I think better answer one in the context the way the last. So let's start to describe the functional reactive programming domain, right? And the first data type used to model this paradigm is time, which is the notion of continuous time, which in F# we use the real numbers. And in this case, we use a record type because it's easier to transform a record type without the mutation. Right? And you can express the same exact data type in C#, a little bit more cumbersome, right? But it's possible, like other language. Now, with a new version, it's easier. You can get how to get the pointer, but you get the idea. Then we have behavior, which is probably the fundamental data type. which is a mention is called signal in other modern computation like L. And so behavior is a polymorphic data type that evolves over time, right? Which means that every given time gives specific value. So in this case, really denoted by the behavior denoted by a function from time to value, right? And you sample the behavior provided at time, it just gives you back a value. Think about the mouse, right? When you click the mouse, this is a discrete event, right? Because you're not controlled that from a user. But the mouse, the movement of the mouse is continuous, right? Which all operation systems or program kind of go against the FRP because treat the movement of the mouse as discrete. But this is the main difference. And in F#, we use a discriminator union to define the behavior. So it's easier pattern matching the behavior to extract the function and the value. And with that simple, types, we can define, few behaviors, right? We have the time behavior, which is just time to time, which is the identity function. We have the constant behavior, which pretty much always you sample, you get the same value back. And like for describe speed, increasing the speed, you have just increase the time. And again, comparing the bit with C#, the certainly doesn't have pattern matching, but you can achieve the same functionality. Right? So you describe the same domain, again, function time to a value t, you can sample, and again with the time, the identity time, the constant function, and increase the speed function. So we can define already a simple API. This is actually from the original paper. And then did the still as much as I could. But you can see we have just a very simple API. We have the leap function, right? Just move the value in the box of the behaviors. And leap 2 and so forth. We have the map function that just map one behavior type A to a behavior type B. And again, with C#. Who likes C#? I mean, no, sorry, no, I'm not the question. Who use C# to work? Okay, so a few of you. So be proud.
I don't like it.
Oh. It's a good one. There are. Right, so, okay. So, this applies both for C# and F#. We can create few functions with the current value. We can create a behavior that just monotonically increase over time because the time continues, right? So it's just a continuous line. We don't always think my calculus. Calculate, this is to calculate the same function over time, right? Which is very useful in animation to make some sort of circular animation. Maybe you're going to use also this function shortly in our code sample. And the current, which is a method with constant here. Oops. Oh, we're going backward. Constant, it just, I create a behavior constant, it just always returns the same value, so just a straight. All right, so we define time, we define behavior, and event, which think about behavior, and we saw are continuous, right? But sometimes they react on some event, right? Some discrete event, which can update an existing behavior or create a new one. An event is the behavior. Event is a polymorphic data type, which can have a value or not. You can see here the time is a pair value, time and option value can have a value or not. And this is think about a continuous sequence of this pair time value ordered by time, right, which is always continuous. If, for instance, we can create an event that fire after 3 seconds and provide an option time of increased speed of 2.5. Otherwise, for example, key press, right? you represent the event here as a pair of time, in this case t0, t1, and so forth, with a character that when you press the keyboard, right? And so really in FRP, you're never really programming against the event. Instead, you deal with potentially infinite events, like a single event, right? But they're ordered by time. So any questions so far? Good. Let's go to some code now. Because now we know how to write FRP, right? All right. So, what time is it? Okay. I can make something sexy now, or something less sexy and sexy later. We'll go for the sexy now.
Yeah.
Yeah.
All right. Whoa. There we go. All right. I go for the ball. So let's go with some. They're not sexy as a bank account, but just to provide an example that you use FRP in other domain. But the sexy one when you see something actually on the screen happening, right? You want to just the console. So let's see with an animation here, and let's start just with. Let's go here and just select. It's pretty easy in F#. Just select the code, run, execute in a tracker, right? All right. Whoa. I know, it's not super sexy, but something sexier coming along. We're building up something sexy. So, how are we building these almost sexy things here? Well, the first line here, nothing really. But we start to define our behaviors, right? So first thing we have this function rotate, take a float as a distance, a speed, and an image behavior, right? And now we're going to go to check behavior, just to see that I'm not cheating. Okay, so this is actually our primitives, right? And I have pretty much exactly what I show you in the slide. Constant time, so it's all right? Nothing really special. But it's start to be powerful. Here, the circle animation, just to come back later, I really create a behavior with a function to go from time, right? From time, you can over the mouse, now give up. Okay, give me time. I don't know if you can see it, but it's the time. Everybody can see the code, by the way? I can make it okay. And this gives us, this some kind of wave shape. The position, I use the circular animation, which just show you, which is just the same. It just, every time you pass every time you sample, because the time is different, it gives you a different value, right? So you just keep moving, okay? The distance here, I use just a constant, because now the circle just moves with the same distance from the point. The lift function, as you can imagine, just lift and apply the function to three different value here that they don't belong yet to the behavior domain, right? Like, forget about that. So just for, let's go to check how this is implemented. That's it, right? By the way, I've been very nice with you. I put all the type, F# based type inference, so even I don't put, that is actually F is a function that goes to R to B, C. We just infer. Yes?
Quick question, just kind of stylistic thing. How typical is it to leave the types inferred and not write them out in production F# code?
So I definitely recommend to depend. If you work in a team, like right now working in a team, I encourage my fellow programmers to put the inference type because you get it right away, right? Mm-hmm. I think that it's easier to refactor the code without inference type. Okay. But I recommend in the end when you're done your code to put the inference type. So yeah, sort of documentation more visual, right? And increase speed here, just take a float, which is the speed, I pipe, which is I compose, right, our function create from the lift tree, and create a new behavior. So the result, the signal to rotate, is be neutral. Alright, so what is better than one circle?
2 circles.
Awesome. Well, even better now. I got another flower, so it's like 5. Whoa. So let's run it first. And then I'm going to go to the cosine. Right? And then this is sexier, and then it's sexier. So this is the flower, right? Whoa. Now, when I click, I change the behavior, the speed, or rotation, right? So now I create this kind of cool effect. And whoa, it's nice. Whoa. So I'm not going to repeat everything here, but I just use the same function we saw here, right? Rotate. I just use a delay in a Y just to give some more rotation. I create a circle, right? I create actually a circle with color. In this case, the constant behavior representing the constant of the distance point, which is a constant, and the color, which is a constant. Now, this is the cool part here, where now I use the merge operator here. Let's go to the definition. So over here. Well, in F# you can create your own fixed operator. In this case, I can go from it. All right. Well, trust me. I want to just be sure to cover also the motion here. So what it does, merge operator in this case, you can imagine, it just take one behavior and merge it to another behavior, you get a new behavior. And you just keep composing it, right? But now, rotate per se is a behavior too, right? So I can, don't click too much. Okay. I can merge these two. I can merge these two rotate operation, right? Now I give a negative value here. So anybody guess what can happen now? No. What's better than one flower? 2 flowers.
5.
Well, hold on here. Now you have 2 flowers, right? And now they just dance together here. But what I think is pretty cool, the fact that because you have the images what a behavior, you merge together the behavior. Rotate is a function, but it's a behavior of you just merge together. Right? And my goal here is not to go through every single line of the code. My idea is just to give you a tease. You can download the code and play with, right? Because a lot of code in the back that I don't have time to cover. But I think that really the composition is what really shine about effortly.
Is it difficult to make your own infix operator?
No. Let's say you have like let's get you have like a list 0 to 10, right? And you pipe it to list filter, right? That's cool, but you can even let's say you want to have like your infix operator actually here. They're going to be I don't know, pipe, caret pipe here, and take a list which is actually I don't need any list filter. And now I create my fixed operator here. If I send to the REPL here, you see, you know that, well, if you can see from there, you will see that the fixed operator from a value to press to a boolean is a predicate list.
The only thing to be aware of with F# operators is you can't really control their precedence. They're
Oh, yeah.
predefined by F sharp.
Yeah, like for instance, if you do something like this, because it's like is equal, there are some precedent that you must be an F sharp programmer. So solar system. This is very sexy. So rotation exactly the same. I have an upper function just to create a planet here. And each planet is a behavior that draw an image. In this case, a circle that I pass a color, which is a constant. They transform the color in a constant here. And the radius also the size. So I create my planet, and I still use my merge operator. What is cool here is the Earth has a moon, right? So I can compose the Earth with the moon, and now, well, let's run it. I forgot to load that.
I do have to say I'm happy to see that you included Pluto.
Yes.
There are scientists that work next door who, they're involved in sending New Horizons to Pluto, and they continue to consider Pluto a planet.
So the interesting thing is that Pluto. So here in the US you have Goofy, right, which is the Walt Disney. In Italy we call it Pluto. So I will never forget about Pluto. I love Pluto. All right, now this so, right, and the Earth with the moon that turn around the Earth, right, which is pretty cool, right? And this is pretty much it by just composing Earth, right? So easy that now you're gonna see me type something super quick. Right, I type though, right? So I create a new planet, Saturn. Now Saturn has a lot of satellites, right? In this case I create a 15 satellite. And which I use the moon. Okay. So I can compose all 15 moons. They are composed with Saturn, right? And then I all merge together using the Factorial Function reduce, right? So let's run it. Voila.
Yes.
That's supposed to go, okay. I have to make
Not to
a
scale.
bounce
Is that what
behavior.
will happen?
But I think the idea is pretty cool.
Who thinks that they were planar?
Huh? Switch operator is here. We're going to cover switch later. I think merge is the okay. But pretty much this is all the API that I use. I don't know why I don't see merge here. Oh no. That's okay. So this is all the primitives I use, right? So and in my experience again is that you build your rich library as all this project here that I have here. But really what you do is that as you go, you just build your combinators, right? You're going to see the final example here using Leap motion that I build a different kind of combinator to deal with different kind of circumstances like bounce the wall, game over, and so forth. The no sexy is the bank account. And the reason, usually I run this first because it's boring and I try to build up. So now I'm going to be like, hey, when I have 6,000, now I have 15 planets, okay, I don't look at that. But still, the idea here is that I'm not going to run it because it's really boring. But the idea that you have you describe your domain, right? You deposit, the withdrawals, the account event, which merge just the two event, you deposit something, you get some cash out. The bank account is a behavior which use the merge event and the accumulator. The accumulator is one of the very useful combinators because I think we're going to cover it, but think about accumulator as a producer of behavior because it's the accumulator function of taking an event, an initial value, an event and give you back a behavior. And every time the event happens, update the behavior. Right? You generally feed with new values the behavior. So you see here, every time you need to get a value, you get to sample the behavior, right? And here's the code. And it's fine. I'm not gonna. Should I run it? No. Tell me. All right. So that was the first implementation of FRP. Any question about this? There is one thing. So I implement FRP in 3 libraries. 2 are in this project. The third one is too embarrassing. I need to leave it. I'm not going to show anybody. So this implementation you can find in the code you downloaded was the original one that I use actually for the bank account example. And that was really to interrupt with imperative language, in this case C#. So I'm not really proud as implemented for the reason that the function applied to behavior and event are not really function because they belong to the instance of the type. However, the cool thing about F#, I was able to extract everything out, use this fun helper, and now I can access the behavior separately, right, as a separate instance. So, all right. Let's go back here. And this was the implementation using the original paper. Who was familiar with this paper? Push and pull. So this is one of my favorite papers. And the reason because I think I'm not the only one here that associate memory, good memory, right, with papers. I'm the only one here. But I really have my Eureka time with this paper because I felt very smart for once. And the reason because I was struggling with the first implementation, with some little glitch here and there. And when I read this paper for the fourth time, actually finally I figured out that what I was reading was the solution to my problem, right? So this paper was written by Conan Elliott in 2007, 2009. And in this paper, really, not really a refactor, but really re-implemented FRP in a more modern approach, right? Introduced concept that didn't exist in the first implementation, such as monads, applicative, and so forth. But most importantly, what really opened my mind is how I was able to revert the pooling model to pushing, right? And if you think about it, there are different benefits using this approach. Think about like a behavior in the first implementation, if it's a constant, never change over time, but it will sample anyways the value together. In this case, no. And also, if a behavior is updated by an event, but an event never happened, why should I resample the same behavior, right? So this is a great paper, and I recommend to give it a read. So this is how I interpret implementation, right? And it works. So in the paper, really refer to reactivity as the notion of reactive values, right? And really, in the paper, we decompose the behavior in 2 components, right? The reactive values, which are independent of time, and time function, right, or reactive values, which are dependent on events. So there are reactive values and no reactive time function. Right? And the idea here is behavior, because now you can treat behavior as a chain of phases, right? And every time an event is materialized, a new behavior is created or updated, right? And these phases are themselves phase, right? So think about behavior now is followed from a new behavior with the time when you make the change, right? Actually, probably this. So you can see now. Oh, I remember what I have here. I have a laser. I'm not that tall. So. So we have a function here, right? The act behavior here is denoted here, which is a function from unit to behavior, right? So this is pretty much a recursive function. In fact, in F# use the rec keyword to denotate a recursive function, right? So then this now behavior becomes this chain of behavior, this chain of phases, which is pretty cool. So it took me 3-4 times to make. So I'm expecting you to get it right away. But I think this is a pretty cool notion that solves several problems that we had in the first implementation. So here we have the, for instance, the identity function of time, right? Time always doing the same time here, right? And give it back the function really the code. Yeah.
I'm pretty certain in this case, but I just want to make certain. The functions that take a unit as an argument, that's just to delay the evaluation.
Yeah, that's correct.
Right? Okay. Thank you.
Good question. Okay, so now cover this part here. So this is the implementation event. So I don't know if it's correct or not. It works. But if you are nice to read the paper and figure out a better way, just ping me. But implemented this way pretty much resemble very much the behavior. Now I just change the correct event. And so for this reason, what's interesting is that in F# and C#, event in F#, event are first-class citizens, right? They're values. So it turned out that honestly, this part I don't really need it anymore. I just need behavior, and I can use the F# event. Right? But again, this is my interpretation. What is interesting, though, 15 minutes. Interesting here is that now we can program a composed behavior in a different way because behavior applicative, right? So there is a pure function, right? And in this case, just a constant. And then I think it's easier if you get this example quick. I'm not going to spend much time because I'm going to jump in a leap motion. But here we have this function. This behavior actually is implemented using the original implementation, right? Which is just a double state behavior to check if the mouse position is inside a rectangle passing the upper the left coordinated and lower right coordinated rectangle, get the position, the correct position of the mouse, and return true or false, right? Using the new implementation now, we can rewrite the same behavior using applicative, right? And the more interesting part is the apply operator here, which will apply a time varying function to a time varying value. I don't know. Let's like it. Combinators here. This is the more important part here. How the combinator now we can create combinator actually to compose event and behavior, like the accumulator here. So the switch operator is the last one I'm going to cover, and I'm going to jump in the demo. So the switch operator is something that I use quite often because the signature here gets a behavior in event with the same type of behavior. But what's happened is that initially you start with this behavior. When an event materializes, is switch the behavior with the two, right? But now think about it. You can write a recursive function and create some sort of two-state behavior, like on and off, or click the mouse, which is pretty cool. All right, demo. So for the demo, I use this guy here, 3D motion. I saw that some of you is familiar, but really is a 3D sensor that detects hand movement, tracks, with finger and speed, and use a Cartesian coordinated, right, with an X and Y for the plane axis and the Y for the particles. What is pretty cool about Leap is that reach under almost 100 frames per second. The API is pretty easy to write against it. The more interesting one is the frame method that is just the side effect of receive the event with the information about your movement. So now you can create, you got the gesture, this wave, you go against the monitor and so forth, and the finger movement and so forth. For the example, I took inspiration from this awesome book, Haskell School Expression. Everybody read this book? There is another awesome book about Haskell, you're coming soon, but this is probably going to be my second one. So, of course, Paul Ratti wrote this book, and there is a chapter, I forgot which one, actually covered FRP in a very light way. As an example in FRP, right, this example about people. All right, so let's run the code, and then we're going to go back to check. Okay, the code here. Okay, now everybody goes to the page. Whoa, so I move my hand, I get the ball. So this is, I think it's sexy because I know what's happening, but think about it. So I move my hand, and everything here is a compositional behavior or mutation or transformational behavior based upon an event. Right? Think about like the ball, right? The direction of the ball is a behavior, is the speed that never change until an event like the bounce, the wall happen, and the behavior switch, which give you different direction, different speed. But also the mouse here, the lift my hand here, and move, which is a behavior, right? That actually is, I'm going to show you later, is used correctly, not as discrete, but as a continuous motion. But even the game is a behavior, because when the ball goes under, well, the behavior is game over. So, how this is implemented, and again, I'm not going to go too much in details here, but a number here, so I put 1 to 10 to remember what should I cover. And again, it'd be very nice to put the typing fair, so you know that conditional exposition as behavior actually is a function flow to ball, right? That it give me a behavior that check whenever the ball is between the left or right wall, okay? And again, in the end, you will see that it's all about creating your behavior that describe your domain and then compose them, which is pretty awesome. I do the same thing for y. It's a bit more complex because y, I have to consider the fact that it can be negative when you pass the paddle and the paddle, but at that level the idea is still a behavior. They go from a function to true or false, depending state. The conditional game over, we start with the true, but whenever the value, the float value that pass is equal or less than -1, it changes the behavior from true to false, which is going to be used in the hand to switch to game over. So leap is a function. This is actually where it produces the value when I move my hand. Leap send me the position, right? Which we're going to check in a second how this is implemented. But so the better approach here, using discrete, the event, using an accumulator and trying to transform the event into behavior. This is a better approach. I don't know if you see it, better approach. But a better one, so the actually is not used. The correct one actually is really used just the behavior. The key precursorily calling the function that actually is called when I move my hand and the leap motion trigger a new position. So the leap motion is up here. Okay. So this is probably the no FRP part of the code, but just briefly, I create a leap motion instance here when the game starts. And the idea of leap motion really is this class here that you need to override some method to deal with the event. What is pretty cool here is that, pretty cool. So the on-frame is part of the API, and we're going to return a controller type. You can probably not see here, but one of the many types here, they give you also the information about your gesture, your speed, your hand, and so forth. Now, because leap motion push up to 100 frames per second, and from some weird design that I don't know the right answer, is not trade safe, I use the mailbox processor built in F#. So now I can access, I can push asynchronously message that are not lost their buffer, but the agent just process one message at a time. And internally, I give you a pseudo right now, and internally I just keep the state in an asynchronous recursive function. Yes?
I'm sorry if this isn't like a good time to ask, but you mentioned the leap motion controller is 100 frames per second. How do you handle something like if you had a game where you wanted a vertical sync or a frame lock at 60 frames per second? How do you handle aligning that with an input that could be, sending you data at a different frame rate than that, more or less?
Yeah, well, so the different approach here, we can talk of after this talk here, but first of all, there are other different frameworks, right? The agent in F# reach about, I think, 25 million messages per second.
Okay.
Per second per minute? Per second, right? Well, something like that. I'm going to give you an answer on that. But yeah, there are different frameworks where we want to use that. Like Homepack.
Yeah, Homepack could be good. Homepack has a way to take live streams or live streams and turn them into cold streams. So basically, you can say keep proceeding one, and you can trigger that stream to actually pull from that. Only take from the eager stream every so often.
Okay.
So on your vsync, you can have it actually produce a value.
So could you take a product of multiple streams and then anything that repeated, it would just get locked by time to, and then it would just anything that hadn't been updated, it would just repeat the same event, right? Okay. Yeah. All right. Thank you.
So I push, the agent always keep track of the last state, and then I expose this API to always get the last value. So pretty simple. We cover this. And here's the last part, right? This is the game engine state function. Takes the time, the initial coordinated of x and y pole and my leap position. So the coordinated here of the pole, I just create a lift value. And you can see here is a bit different because this is my new behavior, right? It's a float, that actually is a float, right? Because we can update. I do the same thing with the y, so I'm not going to cover that. So this is the cool part here. So what's happening here is that I compose with the applied, but everybody can see the code. I compose my behavior because they're applicative, right? So the once behavior is just a behavior predicate, true or false. And whenever this predicate change value from true or false, the event update is triggered. In this case, I just use the identity function because I don't need to update any value, but I just want some sort of notification. That I use here together with the speed, the velocity. The velocity here, I'm going to check how this is composed with the update position of the x. In this case, I use the accumulator here. The 0-3 because when the game starts, you can see slightly move right. And then it keeps producing new value that also updated thanks to the, I leverage pretty much the event, the leap motion trigger, right? And every time this guy is triggered an event, I update all my behavior with a new time. Y, I do exactly the same thing with x, right? So I'm not going to cover this part here. So the last two parts here, which is pretty much the last part of the game, is the game info starts with the initial state that the pass here, the updated coordinated, which is a behavior, which is composed with the y coordinated and the position of my x, right? Now I have my game info that I pass in my conditional exit event. So this function keep the game alive until the conditional game over was the first behavior that we created in the beginning. That was when the value passes negative of minus or equal to -1, it triggered a change state, and then the change state of my game to game on to settle the game over. And that's pretty much it. The library here, I didn't check any of primitive view, but it's all described here in a file. And here there are pretty much is all my library. So all the behavior that I create, not just for this game, like the switch behavior and so forth. I think it's pretty cool the fact that you can create your domain, describe your domain behavior, and just compose them together. And I think it's very sexy. So, to summarize, we saw that FRP, true FRP is dynamic value evolving over time. They provide a simple, pure, composable semantic over behavior. And then I think that the notation semantic, you have to enforce it yourself because I think it's more educational. To don't be sloppy, right? Just create a nice DSL. Don't forget to back up your laptop when you go home. And that's all I got. So. Survey, and this is actually the link you can download all the code and slide. I'm going to upload also in LambdaConf GitHub, but this is also